All right, welcome back. We are now in module number 2, lesson number 2, which is building the EIGRP topology table. This is a really important lesson because it allows us to discuss all of the concepts of EIGRP related to the algorithm itself. What dual is, the diffuse update algorithm, how dual calculates the best routes to reach networks, how we can manipulate those values. So we're going to talk about how the metric works in this particular case. We'll talk about how routing information is received from the neighbors, how that information is stored in the topology table. How do we figure out what the best metric is to reach a destination? And then based on that best metric, how can we interpret whether or not the best path is being used? And then we'll talk about all the other aspects of the dual algorithm, like what is a successor route, what is a feasible successor, what is a feasibility condition, what is advertised distance, and so on. So this is really the theory section, or if you will, or the theory lesson on EIGRP. We'll talk about how EIGRP routers exchange routing information, how they choose the best path in the network itself. We'll talk about how the EIGRP metric is calculated, and I'm going to give you guys a few notes on metric calculation in general. We'll actually go through the process of calculating an EIGRP metric, and then we're going to describe what the feasibility condition is, how the feasibility condition works in EIGRP to prevent loops in the network, and then we'll take a look on and wrap up this lesson by going through and understanding what the EIGRP path selection process is. So in this particular lesson, we're going to use discovery number 3 to go through this lesson and talk about this topology. Let me grab a snip of this diagram here because I want to be able to use this to kind of give you guys some visual cues. Actually, let me grab, not that one, but let me grab the next one here, this one here. Because we need this to kind of express a lot of the concepts that I'm going to be talking about throughout the lecture in this particular section here. So we're going to be using this topology here, and we'll get into some of the details of how we work with this topology as part of our process. All right? So as you can see here, we've got essentially just 2 routers in this discovery. We've got our HQ router and we've got our branch router, but we have several different paths to choose from to go between the HQ and the branch location. We've got an Ethernet WAN connection that goes over network 172.16.1.0. We've got another Ethernet WAN connection that goes over 172.16.2.0, and then we have a serial connection that goes over 172.16.3.0, and that's what our overall goal is here. Now, EIGRP is actually already configured in this topology, so all we're going to be doing is taking a look at the databases, taking a look at the route selection process, how EIGRP has decided to make its decision. We'll take a look at the topology database and see how we can analyze that topology database to be able to identify essentially what's happening in the topology. We do need to drop in our EIGRP configuration on the branch router, but let's go ahead and take a look at the HQ router first and just verify EIGRP operation on the HQ router. All right, that's our branch router. Here's our HQ router. So I'm just going to do a quick show IP protocols and make sure, okay, I've got EIGRP 100 running on this router. We've got an offset list. That's basically just to make sure that the metrics match up with what's in the book. We're trying to manipulate how routes look. We'll talk about offset lists when we get into the route manipulation section of this class, but we can ignore that for now. It's just basically a way that I manipulated the routes to make them look, make the metrics look like what they're supposed to look like in the book. We can see we're using our default K values in this case. We're going to learn more about that in this lesson. We've got automatic network summarization is disabled. We're doing equal cost load balancing, and we're routing for networks 172.16 as well as 192.168, which does include both of the WAN links, actually all three of the WAN links plus this link right here, which is a simulated WAN connection or LAN connection that we're going to be advertising to the branch router. So everything looks good on our HQ router. Let's go ahead and check our branch router and see if we have any configurations enabled on our branch router. Oops. Come on. No IP domain lookup, highly recommended. All right, so let's see, show IP protocols. Yeah, so we don't have EIGRP running on this router. So the first thing is, let's go ahead and do a debug. EIGRP packet. And I want to do the debug just so we can see the process of establishing the adjacency. So you can see here now I'm basically debugging updates, requests, queries, replies, hellos, essentially every EIGRP packet type I'm debugging in this particular case. So I'm going to go into router config T, router EIGRP 100, and we're going to go ahead and put in our network statements, 192.168.1.0. And we don't need a mask for that because that's already a /24. And then network 172.16.1.0, 0.0.0.3. So we're enabling, in this particular case, only EIGRP on this WAN link number 1. And we're just going to take a look at how the adjacency forms. We'll take a look at the metric and take a look at the path selection process, and we'll, just kind of analyze that, and then we'll add additional links as we move through the lesson here. All right. So as soon as I hit return, you're going to see that I'm going to send out a hello packet on that interface. I should also receive a hello packet on that interface. And I should see a neighbor adjacency, and then I should see updates. Not only sending an update, but I should also see that I'm receiving an update from the HQ router. And it should include several different routes. So let's go ahead and hit return. And sure enough, there is everything that I would have expected to see. All right, so let's do an end and an undebug all and scroll up and take a look at what we see here. So I can see as soon as I hit return, it generated a hello packet. We didn't wait for our 5-second window. We sent basically a triggered hello in this particular case. And I sent that out of the interface. I received a hello on the interface as well. And then I added the peer and my neighbor adjacency formed. Once my neighbor adjacency forms, now I can start sending and receiving routing information. So I sent out an update to the neighbor and again, another hello packet. And then I received, so I sent an update, and then I received an update, and again, sent another update. And in this case, I'm actually acknowledging the update that I had received previously. So basically, we're just seeing the transactions that happen or occur kind of on a regular basis between these routers. As soon as I started EIGRP on that WAN link, I sent out and received a hello packet. The hello packets are unidirectional. They're not acknowledged. So I send hellos independent of whatever hellos I might receive on the link. When I did get a hello packet back from the HQ router, I formed that adjacency. We saw that happen. And then I started doing my periodic checks, sending out a hello every 5 seconds. Because this is an Ethernet connection and it's faster than 1.544 megabits per second. All right. Now, unlike hello packets, updates get sent and received bidirectionally. So I send out my update packet that contains all of the routing information, everything that I want to send to the HQ router, and I get an acknowledgement back for that update packet. and then every update packet that I receive, I send out an acknowledgement. You'll notice also that you can see throughout the process that the sequence numbers are correspond to the actual updates that are being sent and received. So we see here, for example, in the beginning of the process, we have a sequence number of 0, sequence 0, 0, and then towards the end of the process, the sequence numbers increment. So we've got sequence number 2 here, sequence 1 here, sequence 2 here, sequence 2, and so on. So you can kind of relate the packets to each other based on the sequence numbers. So here's sequence number 3, which is related to this sequence number here, and so on. So now if I do a show IP EIGRP neighbor, I would expect to see that I'm at sequence number 3, because those were the transactions that were taking place between the routers. We don't typically want to see those sequence numbers increase too much, because that means that there are changes that are occurring in the topology that are forcing the updates to be sent, which means that there's some instability possibly in the process. Another command that we can use is a show IP EIGRP traffic. And we didn't see this command before, but let me actually put the whole command, show IP EIGRP traffic. And what this basically tells me is it tells me all the hellos I've sent and received, all the updates I've sent and received. If I've sent any queries, we'll talk about the query process a little bit later on, whether I've received any replies. Queries and replies are always married together. Replies are sent in response to a query. So it makes sense here that we don't have any replies because we never sent any queries. We do see acknowledgements for updates sent, acknowledgements sent, updates received, acknowledgements received. So this is an interesting concept here. You would almost expect, I mean, this makes sense. Updates received, acknowledgements sent would match up, right? I received 3 updates and I sent 3 acknowledgements. It looks like here that I sent 4 updates, but I only received 2 acknowledgements. So it's possible that a couple of those updates didn't get received at the other side. It doesn't necessarily mean that, but those numbers should be pretty close to each other in the process. So we can analyze, all the packets that are being sent and received, and of course, again, if you really want to identify the stability of your EIGRP autonomous system, you certainly should see hellos and packets being sent and received consistently. You can see that the number is kind of continually incrementing every 5 seconds, but you should not see a continual incrementing of updates and certainly not queries or replies. Any kind of increase in those numbers would indicate some instability in the domain. So the next step would be then to go ahead and check our routing table. We've already verified that we have a neighbor relationship. We've already verified that updates have been acknowledged and sent and received. So the next step would be just to simply take a look at the EIGRP section of our routing table, show IP route EIGRP, and we can see that we have the 2 routes. We have a D route that is the loopback from the HQ router. If we go back to our topology here, the 0.0 subnet is over here, and then we're also getting this external network. So there's some sort of redistribution that's happening on the HQ router to inject this external route into EIGRP, and I can tell that because it shows up as a DEX route. We will be talking about redistribution probably on Thursday. Redistribution, maybe possibly, well, certainly not tomorrow. And we might get to it tomorrow, but definitely by Thursday. Redistribution is essentially the process of taking routes from an external routing domain. It could be a static route, could be a connected route, it could be from another routing process like OSPF or EIGRP, and then inserting those routes into the EIGRP process. In the brackets here, we can see 2 different numbers. The first number in the bracket simply represents the administrative distance of the route. DEX routes have an AD of 170, whereas D routes, or normal EIGRP routes, internal EIGRP routes, have an administrative distance of 90. And then we can see the metric. 409600 is the metric for BR to reach that destination, and we see a similar metric for the external route. Would make sense. We're only going over one link to reach those destinations. So far, everything looks good. Right? Now, later on in this lesson here, we're going to analyze how we came up with that number of 40960. I'm going to show you guys how we actually come up with that number. All right, so let's go ahead now and enable EIGRP on our second WAN link. So we've already enabled it on this link, and now we are going to go ahead and enable it on this link as well. So let's go into BR. Actually, we're going to go ahead and enable it on all three links at this point, I believe. So we've got to put in a network statement for the 2 subnet, and we've got to put in a network statement for the 3 subnet. So let me go ahead and do that on the BR router. Config T. And let's do network 172.16.2.0. Oh my goodness gracious. 16.2.0.0.0.0.3. And we should get an adjacency there. And then network 172.16 3.0. Actually, you know what I want to do? I want to do one more thing. I meant to show you guys this before I did this. All right. I'm going to take that out and get rid of that neighbor adjacency. One of the things that I wanted to show you guys was this concept of administrative distance. We know that we're running EIGRP presently on this link. All right. Which means that, and HQ is running EIGRP on all of its links. Which means that technically from HQ's perspective, this network and this network should show up as, or should at least be part of the EIGRP process. But on BR, it is not part of the EIGRP process. Now, if I go into my BR router, if I do a show IP route, those networks certainly show up because they're directly connected. So we're going to see the 2.0 subnet here. We're going to see the 3.0 subnet here. And even the 1.0 subnet is going to show up as connected. But they are also still part of EIGRP. So if I do a show IP EIGRP topology, I can actually see that all of the subnets are still part of the EIGRP topology. However, 2 of them show up with something called infinity as the feasible distance. In EIGRP, the term feasible distance simply references the metric. FD stands for feasible distance, which means that that is the metric. Any idea why they're possibly showing up as infinity in this case? Any thoughts at all?
No connection to the other side?
No. Good guess, but no. The reason they're showing up as infinity is because, I mean, they do have a metric. We can see this is the next hop, and we're going to get into the topology table a little bit later on, but this is the actual metric for the route. 1564928, and then here 2192456. Those are actually the metrics for those paths. But the reason why they show up as an infinity is because I'm not running EIGRP on those interfaces, number one, and number two, those networks are directly connected to this router. So it's a combination of things. The router knows that it can already reach those networks through its directly connected interface. And because those networks are not running, I'm not running EIGRP locally on those interfaces, that it doesn't recognize those as valid EIGRP routes. So it is inserting a poisoned metric for those particular destinations. So let me go back to EIGRP 100 and go ahead and add network 2 and network 3 in. And see if the behavior changes here. All right, so we got our adjacencies on those two WAN links. Now if I do a show IP EIGRP topology, you will see that they no longer show up as infinity. They're still part of the EIGRP Topology Database, and sure enough, the metric now shows up 153,600 for that one, and 50 was it the 3? Yeah, 515072. I thought it was a different metric before. Let me see if that was a different metric before. Yeah, so that's a little bit strange. Actually, it's not, and I'll explain why that's not strange in a minute. It has to do with the way that the routes are being advertised, but nonetheless, the routes show up as valid routes now as part of EIGRP. Now they're still not going to show up in the routing table as EIGRP because connected routes have an administrative distance of 0. Whereas EIGRP routes have an administrative distance of 90. So the connected routes will always take precedence over any route that's learned through a dynamic routing process, which is why we see the connected routes and not the EIGRP routes. All right. So we've now enabled EIGRP on all 3 links. Before we get into breaking down how we're going to manage this now, and these are the commands that we executed, and we saw the hello packets and all the packets going back and forth, and this is a continuation of the different packets that were going back and forth. Here is the show IP EIGRP traffic that we took a look at, and then finally the routing table where we looked at both of the routes, and then we went ahead and enabled EIGRP on the two additional WAN links. Now we need to get into a discussion of this topology here. It's a very, very important discussion. So let me grab.
Hey, Scott.
Yes, sir.
Real quick. So I've been following along in the Discovery Lab, and for me, when I removed that 172.16.2.0 network statement from EIGRP, it tells me FD is inaccessible. It doesn't say infinity.
That it's inaccessible?
Mm-hmm.
You mean in the topology database?
Yes.
Yeah. It basically means the same thing. They might be running a different version of iOS than I'm running. So infinity basically means unreachable. So that may be just how they're identifying that in that particular case. Does that make sense?
Yep.
All right. Yeah, I don't know what version of iOS they're running in that Discovery. I mean in that Discovery Lab, but basically means kind of the same thing. All right. So let me grab a snip of this. It's a little bit smaller, so we can kind of fit it on the screen here. All right. So when we're dealing with this topology here, it's really important to understand essentially how we handle metrics. And I'm going to kind of go through a process here. It's going to take a little bit of time, but I think it's really important for you guys to understand how the metric is managed and utilized in this environment. So I have a choice, obviously, to get from the BR router over to this network over here on how I decide to go. Am I going to use this link? Am I going to use this link? Or am I going to use this link to reach that particular destination? Now, in order for us to be able to identify essentially which path to use, obviously we're going to have to go through the algorithm. We're going to have to go through a process of identifying essentially what the best path is, and so on. All right? And then we make a decision based on that. So there's a couple of points that I want to make with regard to to how this is selected. And I'm basically going to be giving you guys the information that's on this particular slide here, but I'm going to kind of do it visually rather than just go through some bullet points and try to explain it because this is really a concept that you need to understand from a visual perspective. All right. So let's do a little bit of evaluation on how these paths are being managed and how we're routing between the destinations. So the very first thing that I'm going to check is I'm going to go into my branch router and I'm just going to see what route I'm using. So show IP route EIGRP, and in this particular case, this is the path that I have chosen to reach that particular destination. So I'm going to take that path and I'm going to put it into my diagram here. All right. That is the route that I've actually chosen to use based on that. So first, let's find out how that metric was calculated. I know that we're not talking about the metric right now. We're going to see our discussion of the metric a little bit later on, but and I'll just kind of summarize it right now. The metric for EIGRP is equal to bandwidth plus delay. All right. And we'll actually see the full metric and kind of how it breaks down a little bit later on. But for now, I'm just going to give you kind of the basics. Bandwidth actually has its own formula. It's 10 to the power of 7 divided by the bandwidth along the path. Now, well, let me write it this way. The worst bandwidth along the path in, trying to do this in paint is not always easy, but in kilobits per second. Okay, so when we say bandwidth, we're talking, that should have been a long, but oh well. We're saying in this particular case, I'll fix it, whatever. So you guys can take a screenshot of this if you want later on. All right. We're saying in this case, okay, we're going to evaluate the bandwidth along the path, and whichever part of the path has the worst bandwidth, that's going to be the bandwidth that's going to go into the formula itself. So we have to actually look at, logically speaking, look at the entire path. Can't get this to line up exactly. I probably could have just typed it all over again. All right, you get the idea. So we have to look at the entire path and we have to decide what is the worst bandwidth along the path. Now, this is a very, very important concept that I'm about to describe to you right now, which is that there's two things when it comes to metrics that you have to understand. Metric rules, all right? Number one, only egress values are considered in the calculation. And by the way, this applies to any protocol that is actually doing any kind of metric calculation. Only the egress values are considered in the calculation, meaning the exit interfaces, whatever values exist on the ingress interfaces, don't have any bearing on the metric in that particular direction. Number two, there is no floating point math, meaning no decimals. So any value, calculated value is rounded down to the whole number. All right. So I'll explain what I mean by this as we're going through the process here, but I am evaluating. We've already decided that we're using this link to reach the destination. So I'm evaluating this path to see how I came up with essentially this number here. Does that make sense so far? All right. So I'm evaluating this path to see how I came up with that number, which means now I need to take a look at this bandwidth. What's the worst bandwidth along the path? But that's only half of the formula. The delay piece is equal to the sum of all interface delays, all right, in microseconds. Move this over, seconds. And then we divide that by 10 because we need to make sure that in the formula it's in tens of microseconds. That's part of the formula. We'll see the formula a little bit later on when we get to the metric calculation piece. There is an actual section in this chapter on how metrics work in EIGRP, but I'm just kind of giving you the final story, if you will, of how the metric is calculated. There are K values that are involved, and there's a whole formula, and we can look at reliability and load as part of the metric as well. But this is essentially the part of this is essentially what the metric breaks down to in the end. Okay. So
The bandwidth equals 10 to the power of 7. Where did that 10 to the power of 7 come from?
that's a fixed value. That's part of the formula. It's just part of the formula. 10 to the power 7. It's in the actual EIGRP formula. Okay. And in OSPF, it's 10 to the power of 8. And we'll talk about obviously OSPF tomorrow. But you know, that 10 to the power of 7, it's part of the EIGRP calculation. In fact, let me, since we're kind of going down this path anyway, I'll show you what the formula looks like. I'm not going to talk about it in detail right now, but I will show you what it looks like. And this is essentially what it looks like. All right. Well, that's not a good one because they already filled in the numbers. Let me get one that has the variables in it. Let's do formula. There's the formula right there. Okay. And so if you look at this formula, it looks rather complicated, right? The metric is equal to K1 times the bandwidth, where bandwidth is 10 to the power of 7 divided by the least bandwidth, and that's in kilobits per second, by the way, times K2 times the bandwidth divided by 256 minus the load plus K3 times delay. All of that times K5 divided by K4 plus reliability, and then the whole thing times 256 to tell if it's an EIGRP metric as opposed to an IGRP metric. IGRP doesn't multiply by 256. EIGRP does, because we want to use a 32-bit wide metric as opposed to what IGRP uses. So that is the formula, but remember, well, maybe you do or don't remember, but the K values, the default K values, K1 and K3 are 1, K2, K4, and K5 are 0. So because K4 and K5 are 0, we don't multiply by 0, we simply negate this portion of the formula. And because K2 is 0, we negate that portion of the formula. And because K1 and K3 are both 1, the formula ends up basically being bandwidth plus delay. And that's what I was demonstrating in this particular example. We're calculating the bandwidth and delay. So your question was, where did the 10 to the power of 7 come from? It was written into the protocol. That's how the formula was written. Now, why they chose 10 to the power of 7, I'm sure there's a reason. I'm not sure what it is, but there's always a reason that something is chosen, obviously, especially when it comes to math. So we need to take a look at the egress interfaces, and in this particular case, those egress interfaces are here and here. The loopback interface still counts as an egress interface. So those are the 2 points along the path that are going to affect the metric that we have to calculate. All right. So let me go ahead and back this up, and I'm going to go ahead and get these numbers from a very simple command, show interface. The show interface output includes, and in our particular topology, we are looking at Ethernet 1.0. So for Ethernet 1.0, guess what? There's the bandwidth, there's the delay, there's the reliability, there's the load. So everything that's used in the EIGRP calculation is based on these values. Bandwidth is a theoretical value. It's not a practical value. So it is based on either setting the bandwidth on the interface or it's based on the actual physical interface type. It's not, we're not measuring bandwidth as a throughput. We're measuring it as it's a practical value. If it was measured as a throughput, it would always change, because the loading on an interface might go up and down and up and down. So not so great. And the delay is actually referenced to something. It's not propagation delay. It's not processing delay. Those are all variable delays. It's related to something called serialization delay, which is how long does it take for the data to go from the hardware queue, the TX queue, onto the wire. And that is a fixed value based on the type of interface. So what I do is I just simply copy these numbers, and I'm going to put them on my diagram so that we can then go reference those as part of our exercise here in calculating the metric. So we've captured the values for that interface. Now I need to go to the HQ router and do the same thing for the loopback, because remember, it's only the egress interfaces that matter. All right, show interface. And I'm going to go ahead and go grab my loopback information down here. One more. There we go. And you can see a loopback interface has the same type of information. It's got bandwidth, it's got delay, it's got reliability, it's got load, and everything else. So I'm going to go ahead and put that into my diagram here. And now we have essentially everything that we need to do the metric calculation. All right, we've got our bandwidths, we've got our delays, and we can start putting stuff into our formulas. So the first thing that I'm going to go ahead and do is I'm going to figure out what is the worst bandwidth along the path to the destination. What is the worst bandwidth along the path to the destination? In this case, what is it? What is the worst path, worst bandwidth? The connection on the branch router, right? It's an Ethernet connection, but it's definitely worse than the loopback. All right. So we're going to use that value in the bandwidth part of the formula, because obviously this is a much larger number than what we see on our Ethernet interface. So if I go ahead and drop that into the formula, I'm going to use green in this case. So the bandwidth is 10 to the power of 7 divided by, in this case, 10,000. All right? Because it's in kilobits per second, so I don't need to convert it because it's already written in kilobits per second. And that becomes part of my calculation. So let's, 10,000, yep, that looks good, 10,000. So in this case, the bandwidth portion of our formula is 10 to the power of 7 divided by 10, 1, 2, 3, equals 1,000. All right, probably could have done that in my head, but maybe not. All right, so that equals 1,000. So we've got our bandwidth calculation. Now, what happens if it's not a perfect number? For example, what if it's a T1, which is 1,544 kilobits per second? Well, I take 10 to the power of 7 and, 10 to the power of 7, and I divide that by 1544, I get 6476 dot whatever. At this point, I would just write down 6476. Remember, there's no floating point math, so we are going to drop the remainder. All right? So that's where we're at. We've got our bandwidth calculation. Now the next step is to go ahead and do our delay calculation. The sum of the delays is 6,000. So we'll do DLY equals 6,000 divided by 10, which means that our overall delay is 600. Make sense? All right. And we got 6,000 by just simply adding up the delays, right? The delays are the sum of all the interface delays along the path and divided by 10. Because in the formula, it's in tens of microseconds. See, they didn't show you that here, which is a kind of a big deal. You need to know how delay is actually calculated, and that's how delay is calculated in this case. So now we have to take those numbers and add them.
Run that by me again. I didn't catch that.
Okay, so
The 6,000 calculate.
the 6,000 is the sum of all the delays in microseconds. So we can see that it's already written in microseconds from the show interface output. And it's 1,000 there, plus it's 5,000 there. So that's our 6,000, because we're only doing the egress interfaces, not the ingress interfaces. And then we have to divide by 10, because in the formula, it's tens of microseconds, not microseconds. Again, that's just part of the formula, okay? It's in tens of microseconds. So I have to divide by 10, and that's where I get my 600. So if I take my 1,000 plus my 600, and I multiply that times 256, I get 154,600. Now, that's not what the metric shows here. I'm going to show you why that's not the metric that we see here, but that would be the metric for that particular path for the 192.168.0.0 subnet. The magic doesn't happen here because we're manipulating the metrics for the purpose of the class and for the purpose of route selection and path selection. But let me go ahead and write that down, and I'll show you why so that would have been my overall path metric, but I'll show you why that metric isn't the correct value. In fact, let me show you right now. If I go into my HQ router and I do a show run section EIGRP, you're going to see here that we're actually doing offsets for the different links here. Although that's interesting, we aren't doing an offset for WAN link number 1. We're only doing an offset for WAN link for serial 20. What did I do wrong? Let's take a look here. There's a couple ways that we can analyze this as well. If I do a quick show IP EIGRP topology, the loopback 192.168.0.0 128.256, that makes sense, because if I take 10 to the power of 7 and I divide that by show interface loopback 0, I divide that by this number here, I get 1.25, so that becomes a 1. And the delay, let me try that again. No, that makes sense, because this number is bigger than 10 to the power of 7, and the delay is 5,000 microseconds. So let's do 5,000 divided by 10 times 256, 128,000. So we're not manipulating anything here. All I did was basically do the exact same calculation that I just showed you guys, but I did it locally based on just the local numbers here. We always drop the decimal point when we're doing our bandwidth calculation. So we dropped to 0.25, which means that basically the bandwidth became 1. And then the delay was 500 times 256, which gives us our value here, 128,256. Although it didn't give us 128,256, did it? It gave us 128,000. I think that's what it did. 500 times 256, yeah, 128,000. What's going on here? Dumb. All right. So I figured out what the heck I was doing wrong. Let's go back to our diagram here. Because I took the 256 and I multiplied it after I added the numbers together. But what you have to do, the way it works in the formula, is you have to multiply each of the values by 256 and then add them together. You can't take 1,000 plus 600 and then multiply that by 256 because that's a different product than if you take 1,000 times 256 plus 600 times 256. So let's do it the right way now. 600 times 256 is 153,600. So that becomes the delay portion of the formula, 153,600. And then if I take my bandwidth, 1,000 times 256, that becomes my 256,000. See if I can squeeze that in there. And then I add those two numbers together, and that's gonna work out a lot better for us. So 256,000 plus 153,600. And how about that? 409,600, and that's exactly what we have for our metric. So I apologize. I don't know why. I kind of skipped ahead a little bit and didn't do my math the correct way, but that's how we got the metric. 409,600 makes perfect sense. But again, remember, if you look at the formula, the way that the formula is written, they're distributing this multiplication across the entire formula. They're not taking that value and multiplying it by 256. You have to actually multiply each value by 256 and add those numbers together, and that's what results in the appropriate metric calculation. So, that being said, we know that the metric for that particular path is 409,600. Now, I can actually take that and I can take a look at the other paths as well and see if, now we do have the offset applied on this bottom link here, so we'll have to make sure that we include that. But I can actually see and predict how EIGRP is going to behave based on the calculations here. So let me go into the branch router again, and let's go into the, what's going on here, branch router, and take a look at this interface right here, Ethernet 1.1. All right, so if I do a show interface Ethernet 1.1, I can see that the bandwidth is set to this value and the delay has actually been modified. If I do a show run interface Ethernet 1.1, you can see that we've actually modified the physical delay of the interface to affect the metric, which is why we're not load balancing. I mean, if I took that out, I'd end up load balancing over that circuit path. So I can actually predict, now based on this number, I can predict what that metric is going to be. I'll drop this in here. Oops, let's make that red so it matches. I'll drop that in here and can't really, I guess I can kind of try and sneak it over here so that we can then go ahead and calculate what the metric for that path might be. All right. So as far as the bandwidth, is it going to change? No, because the bandwidth for this path happens to be the same as the bandwidth for this top path here. So that's not going to change. I'm going to go in and not do that. I'm going to go in and let me just move this over so that we kind of can identify, you know, that that's for that link there. All right. So this is this link here. And this one is this link here. All right. So what changed as part of this metric? Just the delay portion changed in this particular case, right? So now let's go ahead and calculate what the delay value would be for this second link. I'll use blue in this case. And the delay value for the second link would be DLY equals the sum of the delays, which is 10,000. You guys understand how we got that value, right? Divided by 10, which is going to end up being a delay of 1,000. 1,000. You guys understand how we got the 10,000, right? We're just adding up all the delays along the path. I typed 50,000. Was it 50,000? I thought it was 5,000. on that interface. Oh, it was 50,000. So, all right, let's fix that. So this was actually 50,000 plus 5,000 is 55,000, right? And we're going to divide that by 10, which means that the delay is 5,500. All right, does that make sense? So far, so good? All right, so we go ahead and do our calculation then. And I take my 5,500 times 256, and I get 1,408,000. We'll put that number down here, which means that in this case, the metric for this path should be that 1,408,000 plus the 256,000, which is 1,664,000. So I'm going to go ahead and put that in for this path. So this is the, oops, I didn't copy it. This is the metric for this path here. How can I test that, by the way? What's the quickest way I could see whether or not that's accurate? Any ideas? Well, I won't see it in the routing table because it's not the best path, right? I can look at my database. If I go into my topology database, I should see that as an option, show IP EIGRP topology. Because remember, the topology database includes not only the best path, but the second best path, the third best path, and so on. And sure enough, there it is, 1,664,000. All right, there's our best path, there's our second best path. So already we're analyzing the topology database. We've gone way beyond, well, we're kind of getting into where we're supposed to be. This is the best path, which is called the successor, by the way. And this happens to be the next best path because it has the second best metric. Okay. Now let's do the exact same calculation for the third path. All right. I got way too many windows open here. Let me get rid of some of these.
As far as the delay is concerned, does that have anything to do with the flow of traffic, or is it just a number for calculation's sake?
The delay is it's actually related to something called serialization delay, and it doesn't have anything to do with propagation, processing delay. It's a fixed value that describes how long it takes for a packet to go from the transmit queue of the router onto the wire, and it's solely based on the type of interface. So it's a fixed value.
Dynamically. Okay, it's determined dynamically though, right?
It is determined dynamically based on the type of interface. So gigabit Ethernet interface will have a specific delay, fast Ethernet will have a specific delay, and so on. Make sense? All right. So let's go ahead and do the calculation one more time. All of this is great. I mean, it's not part of this particular discovery, but it is good to kind of see this as we move through some of the other discussions here. But we do have three paths. Problem is the third path doesn't show up here, and I'm going to talk about why that's the case in a minute. But let's go ahead and at least do the calculation for that third path. So we're going to take a look at serial 2.0 in this case now on our branch router. Show interface serial, actually it's not serial 2.0 in our topology. Oh, it is. Okay, excellent. So show interface serial 2/0, and we've got these values here. So it looks like we've manipulated the bandwidth in this case, but we haven't manipulated the delay because the serial interface clearly doesn't have a bandwidth of 800,000 kilobits per second. In fact, if I do a show run interface serial 2.0, we can see that the bandwidth has been applied. So you can manipulate the metrics by changing the bandwidth and the delay on an interface. It doesn't affect the actual bandwidth of the interface. It doesn't affect the actual delay of the interface. It just simply changes how the router interprets that information. All right. So let's go through and go in and do our final calculation here. I've got the bandwidth and delay for this interface. We'll go ahead and do this one in orange. And we'll do this one in purple. So we've got the, oops. Wait, is that cut off? No, somehow it didn't copy the whole line. Let me go, oh, because I had copied this statement down here. Let's grab that right there. And let's put that in our formula here. So we've got bandwidth and delay. That's too close to the other color. Let's do, we'll do brown. All right. So we got bandwidth and delay for that interface. We can assume the loopback is going to be the same, but there is something we're going to have to do to kind of calculate this, because we've got the offset being inserted into the metric as well. Let's assume, well, we know that the bandwidths are the same. Actually, this bandwidth is a little bit worse. So the bandwidth portion of the formula is going to be this number. So bandwidth is going to be equal to 800,000, sorry, 10 to the power of 7 divided by 800,000. And then we're going to take that value and then we're going to multiply that value times 256. So 10 to the power of 7 divided by 800,000. So 12, essentially. And we're going to take that number and we're going to multiply that times 256, which equals 12 times 256, 3,072. All right. Oops.
And that decimal dropping that 30 point, that happens in the middle of the equation.
Yes. Yeah, you do not multiply. Every individual calculation is a whole number. So you do not multiply the remainder with the 256. You always drop the decimal within the specific product or calculation that you're trying to calculate. So we've got a bandwidth value of 3,076 or 3,702. And our delay is the sum of the delays in microseconds, which is 20,000 plus 5,000. So the delay portion of the formula is 25,000 divided by 10, which equals 2,500. And then we multiply that value times 256. All right. And so we take our 2,500. What happened to my calculator? There it is. Take our 2,500 times 256. So 1,048,576. All right. Now, if I add those two numbers together, that would be my metric. However, and it gets a little bit complicated here because we're doing an offset. My metric is not going to be this 1,048,576 plus 3,702 because of the offset that I have on the HQ router. And normally you would not configure an offset. It's just something that was done in this particular exercise to make it match up with what's in the actual book. So if I do a show run section EIGRP, I'm actually changing the metric 255871744. Basically, I've created an offset list. There is also a, if you look at the config here, there is a access list that takes both of those routes, and then we offset out of that serial interface. We're offsetting the metric that's being advertised to the neighbor on that interface by this amount. So essentially what I'd have to do is I would have to calculate just the local metric of that route, which I did here, and I would add that offset. So let me see if that actually works. Hopefully it'll work. So let me go ahead and add 3702, and then I go ahead and add the offset, which was this number here. And I don't know if this is going to work or not, but we'll see. And that becomes the metric. So we basically just negate whatever's coming from the neighbor, and that becomes the metric for that path. We'll go ahead and put that in, and then we'll go verify it. There's a reason why that offset is there, by the way. It has to do with feasibility condition and discussing the concept of feasibility condition. So that becomes the metric for that path. Now, let's go ahead and find out if that's actually true. All right. If we go into our branch router and I do a show IP EIGRP topology, we don't see that path even listed, right? It should show up right here. We should see all three. We haven't talked about this concept yet, but there's a concept in EIGRP called a successor and a feasible successor. All right. And the offset was put in place to override, because essentially the metric for that loopback would have been this number anyway, because it's the same values no matter what. This is called the advertised distance, or some people call it the reported distance. That is the metric for my neighbor to get to the same destination. So essentially this is the metric that's being advertised by my neighbor for this network. And then this is the total path metric, which includes the cost of the link between me and my neighbor. So the first number represents something called the feasible distance, which is the entire path cost, whereas the second number only represents the cost for my neighbor to reach the destination. So you guys would probably agree that in all three cases, that neighbor's cost is going to be the same because it's a loopback tied to this interface, right? And that's totally true, but except we have the offset, all right? So what we have to do is we have to do a show IP EIGRP topology all dash links so that we can see that path as well. And sure enough, here is the path. The metric is 256.514.816. Was that what we calculated? 256.924.022. So the math didn't quite work out. It's pretty close, but you know, with offsets, there's a couple of other things that need to be involved in doing the calculation. So in our particular case, it's close enough for government work, but you guys understand fundamentally how metrics are calculated. When you're adding offsets, there's a couple of other things that you have to consider. For example, and actually I know why the number's not correct now, so let me go ahead and fix it. The number's not correct in this case because with an offset, I'm not going to consider the delay from this router here. So when I go in and calculate my delay, I'm going to have to recalculate this without the 5,000 because of the offset essentially overrides anything that I would be receiving from that router. So 20,000 divided by 10, delay is 2,000. Multiply that times 256, and 2,000 times 256, 512,000. So that becomes the delay value, 512,000, and I add that to, well, I've got to take my, no, I add that to my, that doesn't make sense either. Oh no, that's right. Got to add the offset. So I take my 512,000 and I add my 3702. So that becomes essentially the local metric. And then I add that offset, which I got from the HQ router, this number here. Plus that number. Does that look better? I don't know. Let's see. 256.514.816, 256.387. That's closer. It's closer. Anyway, we don't have to spend a whole lot of time on that. Offsets always kind of throw things off a little bit, but because we have an offset here, we'll just kind of forget about that link for now with regard to the metric itself. So let me just change all this back, and we'll just kind of leave that number based on the calculations. Actually, I'll just make a note here. Offset list applied. So if you're looking at this later on and you're trying to figure out, well, how the heck did I get that number? Because it doesn't match the rest of the formulas. So we'll just put an offset list applied there. And for simplicity's sake, let's just make this number match what's in our actual topology database. This is the overall path metric. So we'll put that in. Now, great. All that being said, I think you guys have a pretty good understanding, at least about how the EIGRP metric works. Offsets aside, you understand how an EIGRP metric works, okay? Egress interfaces, no floating point math, bandwidth 10 to the power 7 divided by the link bandwidth in kilobits per second, but it's the worst bandwidth along the entire path. Multiply that number times 256. In fact, I'll just put this times 256 here, and I'll put a times 256 here. All right. And delay is the sum of all the delays in microseconds divided by 10, because we want it in tens of microseconds. Multiply that times 256. Add the numbers together. That gives you your overall path metric. Whew. All right. So we know why we're not load balancing, because WAN link 1 has a lower metric than WAN link 2, which has a lower metric than WAN link 3. All right. So now let's start finalizing all of these concepts on the diagram itself, right? So the first thing we need to understand is what is the successor path. And let's do, where are my font tools? My font tools. Now let me change the font. Oh well. Let's do Control B. So this becomes my successor path. And the successor is essentially the best path, which is the one with the lowest feasible distance. These are all terms that are part of the dual algorithm. So the successor path is the best path. It's the one with the lowest feasible distance, which becomes this path here. All right? And because this path has the lowest feasible distance, it is the successor path. That is the FD for this particular path. Make sense? All right. This path here becomes something called a feasible successor. Let me see, I'll put it over here. Feasible successor is the second best path. Best path, as long as it meets the feasibility condition. So must meet the feasibility condition. All right, we'll talk about what that feasibility condition is, but in this particular case, this path definitely meets that feasibility condition because of the way that it's calculated. Let me clean this up a little bit. So this is my successor path, and this guy over here ends up being my feasible successor path because it meets that particular feasibility condition. Well, that looks like crap. All right, I'll just draw a little line. All right, so this is my feasible successor because it meets the feasibility condition. What is that feasibility condition? It states this. All right, I'll put it up here. FC is a loop avoidance mechanism. It has nothing to do with actually choosing the best path. It's simply a loop avoidant mechanism that allows us to identify whether or not the alternate path is part of the primary path. All right? And here's what it basically states. The reported distance of the backup path must be less than the feasible distance of the primary path, what we call the successor. All right, that's what the feasibility condition states. The backup path, which is this path here, WAN link 2, that metric, or that the reported distance for that path needs to be less than the feasible distance of the primary path. So we already know that the feasible distance of the successor is equal to 409,600. You guys agree with that? Feasible distance is the metric, and that's 409,600. The reported distance of the feasible successor path, in this case, do you guys remember what it was? Well, we can see that in the topology table here. What is the reported distance for the 192.168.0.0 network from router 2, or over the 2 link, the 2 subnet? It's the second number. This is the value. This number here has to be less than this number for it to meet the feasibility condition. And it is, right? So in this particular case, that number is 128,000, what was it? Timed out. Show IP EIGRP topology. 128,256. All right. Are you guys following? I know it's a lot of information, but remember, this is what makes the difference between a network administrator and a network engineer. I mean, this is.
Yeah, I was confused about the reported distance until you went back and said that it was neighbors.
It's essentially the neighbor's cost to reach that destination. Exactly.
Correct.
Yeah. As long as that cost is less, then this path can now qualifies as a backup path. Now, it doesn't mean that this path down here can't be used, but now we're getting into the whole concept of what happens if path 1 fails, and then path 2 fails, and so on. All right. We definitely know that the third path does not meet the feasibility condition, because if I do an all dash links, I can see here that the reported distance is way higher than the feasible distance of the best path, and that's because of that offset that we added. So this number would be added to whatever metric we calculated locally, and that's what we get to our overall path metric. But clearly this path does not meet the condition. All right. So I don't want to get into the whole concept of the failover just yet, because we still have a couple of other things to talk about. But overall, I hope that overall this makes sense. I mean, you look at the diagram; it's maybe a little confusing, but this is the algorithm. This is dual. This is what's happening, and this is how EIGRP is making a decision. So in your book on page 100, they go through the whole concept of, okay, we've got the metrics 166,400 for the middle path and 409,600 for the top path, and everything seems to match up. But what does it mean to have a feasible successor? Rhetorical question. What does it mean to have a feasible successor? This is what it means. If for some reason, let's kind of make this match up too. If for some reason this path fails, let's say this link goes down or whatever, the convergence time for EIGRP is almost instant because it immediately starts routing over this path because it's already selected the next best path. All right. So in order to ensure that EIGRP can converge as quickly as possible, you want to make sure that you have a feasible successor, even if you have to trick the router into thinking so. Remember, all of this whole concept of loop avoidance and the need to even identify whether there's a loop in the network or not is because EIGRP is a distance vector routing protocol. And as a distance vector routing protocol, it just simply doesn't have the same visibility about the network that everybody else has, right? It's not a link state routing protocol, so it has to make certain assumptions on what the topology looks like. So all of this whole thing about the loop avoidance mechanism, this feasibility condition check, that's all because EIGRP is trying to make sure that I'm not going to be inserting a path that's part of the original path. And in this case, it's definitely not. This link is a completely independent link from this link. So if this link fails, then we'll go ahead and immediately start routing over this link. And we're going to demonstrate that in a second. But what about the third link? The third link does not meet the feasibility condition. This bottom link, WAN link 3, doesn't meet the feasibility condition. So can it be used? Right? And it is still a valid path. You're not going to look at it and say, well, yeah, if WAN link 1 and WAN link 2 fail, what, do I just not use the bottom link? No, that's not what happens. The answer to the question is yes, but only after a secondary check takes place, right? And that secondary check is the query process. Query/reply. All right. So essentially what's going to happen is if WAN link 1 fails, we'll immediately start using WAN link 2. But if WAN link 2 fails, HQ is going to say, well, this metric is so high that it could potentially include the original path. So I'm going to send a query over to the branch router on that link, and I'm going to say, do you still have a route? I'm going the other way, sorry. The branch router is going to send a query over the serial link to the HQ router saying, do you still have a route to the 00 subnet? The HQ router is going to send a reply, and then that route gets inserted into the routing table. Make sense? That's the only time these query processes take place, is if a primary link fails and there's no feasible successor, then I query the remaining neighbors to see if they still have a path to that particular destination. All right.
What kind of outage time do you think that would be?
Oh, we're talking about microseconds for the feasible successor. We're talking about depending on the depth of the topology, and we're going to get into the query process, but it shouldn't take more than a couple of milliseconds. Especially in this particular case, it shouldn't take more than a couple of milliseconds. But yeah, that's essentially the way the process works. In fact, I'm going to demonstrate that, and you can see how quickly the route gets inserted into the routing table. All right, and we'll take care of that in a minute here. All right, how you guys feel about all the theory so far? I mean, we've essentially pretty much covered, outside of stub routing, which we haven't gone through yet, we've essentially covered really what EIGRP is all about in a lot more detail than even the book goes through. But So they do show us on page 100 of the book, you know, what does the routing table look like? And of course, we know that we're going to be using the top path with a metric of 409,600. Actually, let me go ahead and flip through the slides here. All right, so there's the topology. When you're doing a show IP EIGRP topology, remember, you're only seeing successors and feasible successors. You're not seeing the links that don't meet the feasibility condition. All right, and we can also tell that this is clearly going to be the best path. It has the lowest feasible distance. This is the next best path that meets the feasibility condition because the advertised distance is less than the, or reported distance is less than the feasible distance of the primary path. All right, and we look at the routing table, and sure enough, the 409,600 is the route that's inserted into the routing table because that's the best path. There is a third path. So if I do a show IP EIGRP topology all dash links, I can see that third path, 256.00000. That's the reported distance because of the offset that we have applied in the configuration. And the overall path metric is 256.12000.
On your screen?
Sorry?
I can't see the stuff you're saying on your screen. All I see is the...
It's the highlighted piece right here. You see the command show IP EIGRP topology all dash links? Are you not seeing my screen?
No. All I see is... I can see. He's not in a routing. He's looking at the book.
No, I'm just showing you the slide, right? Because we already looked at all this stuff in the book. I mean, in the router. I'm just showing you the slide, right? So this is the branch router. This is the command show IP EIGRP topology all dash links. The highlighted one here, which is 172.16.3.1, that's that third path, the WAN link 3, and we can tell it doesn't meet the feasibility condition because 256.00000 is higher than 409,600. Okay, are you seeing what I'm pointing out now? I want to make sure my screen's refreshing correctly.
No, I'm not seeing your screen change. All I see is this.
Well, no, I'm not changing my screen. Do you see my little hand moving around on the screen, my little cursor?
No, I don't.
Do you other guys, does everybody else see it?
Yeah, I see it. Maybe that's...
I'm wondering if his WebEx... Well, I'll tell you what, did you just see my slide change?
No, I didn't.
Okay, something's going on with your WebEx then. Let me pause the video. So now what we're going to do is we're going to take a look at what the impact is of having a feasible successor versus not a non-feasible successor. So we're going to do a ping from the branch router to that loopback interface. So let me get into my branch router here. All right, and I'm going to have to do this a couple of different ways here. I ran into this in the last class because we don't actually have a physical router here. So I'm going to telnet to the branch router from HQ. What's my address? That diagram is wrong. I just noticed that. It got the same subnet on both loopbacks. That's clearly not right. Let me just grab an IP address for my branch router that I can telnet to. Actually, I'm going to have to configure my enable password and my line VTY password, Cisco login. Do show IP interface brief. I'll just telnet to well, I got to telnet to an interface I'm not going to turn off. I'll telnet to 3.2 for now. Okay, so 172.16.3.2. So I'm going to start a ping on my branch router, and then I'm going to shut down on the branch router. I'm going to shut down the interface that goes over from the branch router over to the HQ router, the top link. So let's start our ping 192.168.0.1, and we'll do a repeat of 10,000, and we'll do a size of 1,000 bytes. All right, so my pings are going now. Now I'm going to go ahead and shut down, show IP interface brief. I'm going to shut down this top link, Ethernet 1.0, config T, and I'll do a quick shut, and let's see how that affects our pings. All right, notice, well, it doesn't look like we lost one ping right here. Let me break the ping. We lost one ping right here, right when the interface went down, but you saw how quickly the route updated, right? Because we had a feasible successor, and the route updated very quickly. Now let's get into the process of what's going to happen. First of all, let me do a show IP EIGRP topology just to show you that we've now gone over to this route. We're going through the 2.1 link. So I'm going to shut down that interface, Ethernet 1.1, and see what happens with the ping in the case of the fact that we don't have a feasible successor. Actually, before I do that, show IP EIGRP traffic. Notice here, queries were sent and replies were sent because of the topology change. And that's because we do have a third path that didn't meet the feasibility condition. We're still using the feasible successor, but in the case of the backup path, we still want to verify whether or not that backup path is still valid. Even though we're not using it, we're still going to generate the queries and on that WAN link number 3 to make sure that that path is valid. So let's go ahead, and we should see this number go up again. Once we shut down the second link, we should see a query go up, the query process increase, and the replies increase as well. So let's go ahead and start our ping again. And now remember, we don't have a feasible successor. All right, do show IP EIGRP topology. We don't have a feasible successor. If I do all dash links, we can definitely see that that other path exists. We can definitely see the other path is there. So I'm going to go ahead and shut down Ethernet 1.1, interface Ethernet 1.1, shut it down, and let's go take a look at our pings. All right, and let's break it. So did we lose any packets? We did. We lost another packet, actually right here. Actually, that was when I canceled it. So we did lose another packet. All right. So you can see it still doesn't take a whole lot of time to do the query process, but in this topology that makes sense because there's only one neighbor I have to query. Show IP EIGRP topology. And we can see now that we've actually inserted this route as a primary route. Show IP EIGRP traffic, and we can see that we generated another query, a fourth query, once the path went down. All right. So
Can you scroll up to the last time you did the EIGRP topology?
yes, sir. Talking about this one right here, right?
No.
Oh, prior to shutting down the second link.
Yeah. Because the reported distance in that one was
Still
definitely more.
Still the same. The metric went up because remember the metric for that path is 166,400, but the reported distance is the same because it's the same loopback in both of these cases.
That output wasn't what I was talking about.
Oh, you're talking about the all dash links.
Okay, maybe that's what I was talking about.
Yeah.
All that one still has it. It's going to always have it.
Yeah, it'll always have it. Even if it's not a feasible successor, you'll still see it. Obviously, if I do a show IP EIGRP topology now, even if I do all dash links, it's not going to show anything because there's only one path remaining in this particular case. So it's still a valid path. We could still use it, but we have to go through that secondary query process. All right. So that essentially was really what they were trying to demonstrate in this entire exercise. And you can kind of see the process that they went through here was the same process that we went through. Here's all three routes in the database based on all dash links. And this is a continuation of the topology table from the previous slide. They do their ping here. They went ahead and they shut down the top link to indicate that a link went down. They did it on the HQ side, but I do it on the branch side because I don't want to wait for the dead timers to expire, because then you see the dead timer expire here. I do it. Now they actually lost 1, 2, 3, 4, 5 packets. We only lost 1. All right, but in any event, you're going to lose something because you're actually literally changing the route. But in our case, we didn't lose that many. And sure enough, we can see now we're going over that WAN link number 2, which has a metric of 1664000. If I look at my topology table, that's the route that's inserted in my topology table, but I don't have a feasible successor in this case, because the third path doesn't meet the condition. So then they started the ping again. Now they shut down the next path. All right, so now we only have one link available. And again, you see lost packets about the same, 1, 2, 3, 4, 5, 6. So they lost one more in this case than they did the previous time. The point here is that that third path is still a valid path, and the query process doesn't take a significant amount of time to happen. So we're seeing about the same failover time. But very important to note that that's not always going to be the case. The density and the depth of your network topology vastly affects how the query process takes place and what happens within the query process. So it's really important to understand that aspect of it. I just saw in the chat window, Jason, you had put in redistribution statement with a route map.
Yeah, so it was completely different in the Cisco lab versus the lab that you had in terms of how they were.
Oh yeah, and in terms of how they were manipulating the route. Yeah. So they were doing a route map, and they were redistributing the route and then injecting the values of the metrics in. I could actually take that information and update my file so my numbers match up. But yeah, thanks for putting that in there. I just saw that. I don't know why, but all right. We'll talk, of course, later on about the effect of queries on an EIGRP domain and why I might want to be concerned about the query process, because it is definitely something that you need to be concerned about. So now we see that in this case, the third path is now being used as part of the path, as opposed to the first two, which are now shut down. Yeah, that's basically the end of that part of the discovery. So let me see what we have left in this particular. So as far as exchanging routing information, a couple of points that they make here. Only the routes used by EIGRP are advertised, meaning that basically only the interfaces or the networks that are included in the EIGRP process get advertised. We're not going to advertise connected routes unless they're part of EIGRP. We're not going to advertise static routes unless they're redistributed into the EIGRP process. So we obviously know that we enable networks to participate in EIGRP by using one of two methods, either by using a network statement to include specific interfaces in the EIGRP process, or by using some sort of redistribution, which we'll learn all about redistribution a little bit later on. All right. Redistribution is basically a way of taking routing information from one source that's not part of EIGRP and then inserting or injecting those routes into another routing protocol. We spent quite a bit of time already talking about the metric as well. The metric weights, or the K values, allow us to determine how much weight we apply to each component of the metric: bandwidth, delay, reliability, and load. But as we saw from the formula, bandwidth and delay are the ones that are used by default because of the default K values. Cisco doesn't recommend ever changing those K values, and there's really no practical reason why you ever would. I think in the initial onset of implementing the protocol, it was determined that the more granular the metric can be, the more accurate it can represent the path, which is kind of true, but there's only so much granularity you need to make it actually work. So in this case, we just simply rely on bandwidth and delay. What the book doesn't tell you, though, which is the pieces that I told you, is that number one, only egress values are considered. Number two, there's no floating point math, so you always drop the remainder. And then, of course, you guys saw from my mistake, you need to multiply each component of the metric times 256 before you add the values together, as opposed to adding them together first and then multiplying by 256. All right. And so they go through a couple of different examples here. K1 and K3 are equal to 1. K2, K4, and K5 are equal to 0. See, this is why I did it. Bandwidth plus delay times 256, that actually doesn't work, right? We tried that. I guess in this particular case, should that work? Yeah.
No, they're adding them up and then.
Yeah, yeah. I mean, we saw that was not. I mean, if I take 1,000 plus 1,000, and then I multiply that times 256, it's 512. But if I take 1,000 times 256, and I multiply that times 2, that's 512. So I don't know what the heck I did wrong. Math should be the math. I'm not smarter than a fifth grader, so you know, my math is not that great. But anyway, make sure you multiply the values times 256. I must have screwed something up and just multiplied incorrectly or something like that. But we talked about the bandwidth is 10 to the power of 7 divided by the minimum bandwidth along the path in kilobits per second. And again, no floating point math there. If you get some sort of remainder from this calculation, you need to drop that remainder. And the delay is the sum of all the delays in the path in tens of microseconds. Now, there is one other thing that I want to mention, because I didn't show you guys this before. We already know that we can manipulate. Let's get rid of that there. Make sure I'm in the right router. So I can manipulate the path metric by going into an interface. So let's do a show run interface Ethernet 1.0. In this particular case, I can go into interface Ethernet 1.0 and I can set the bandwidth, and that value is already in kilobits per second. Setting the bandwidth affects things like QoS, it affects metric calculations and so on, but it doesn't actually change the operational bandwidth of the interface. The interface is still going to function at its normal line rate speed. But if you're setting the delay, if you put in a delay of 10, you're actually setting the delay to 100. And that is because, and I don't know why Cisco did this, but when you set the delay, it's in tens of microseconds when you use the delay command. And it's in tens of microseconds in the formula, but it's in microseconds in the show interface output. So if I set a delay of 1,000, I do a show interface Ethernet 1.0, I actually set the delay to 10,000. So just keep that in mind. When you're setting the delay, you're actually setting it in tens of microseconds, not microseconds. All right. Show interface allows us to see that information. And then they go through a couple of examples. They're looking at the bandwidth along this path, the top path. The worst bandwidth is 10 megabits per second. The cumulative delay is 40 plus 10 plus 50, which is 100. Put those into the formula. And then that allows us to calculate the bandwidth for that particular path. In this case, they're doing R1 to R2 to R3 to R4. Minimum bandwidth is 10,000 kilobits per second, which is 10 megabits per second. The delay is 4,000 plus 1,000 plus 5,000. I wish they didn't do this. They're confusing the scenario here because they put it in milliseconds, but in a Cisco router, it's in microseconds. And in the formula, it's in tens of microseconds. So now they've got three different numbers that they're trying to confuse the situation with. But anyway, 40 milliseconds does happen to be 4,000 tens of microseconds. And 10,000 milliseconds is 1,000 tens of microseconds, and so on. So you just put it in the formula. Notice that they did multiply the 256 times each value here. And 10 to the power 7 divided by 10,000 is going to equal 256, 100,000. Multiply that times 256. 4,000, 1,000, 5,000. Since they've already converted it to tens of microseconds, you just multiply that number and that equals that path metric. Okay? Then they do the same thing for the bottom link, same numbers. So we can see that this path has an overall metric feasible distance of 2,816,000, whereas the bottom path has an overall feasible distance of 1,843,200, which means the bottom path is going to be my successor. Now let me ask you guys a question. All right. Does the top path meet the feasibility condition? Well, we don't have enough information so far to figure that out, but we do have enough information on the diagram to figure it out. All right, so let's run through that exercise real quick. I don't usually do this as part of the calculation, but let's go ahead and do it. Remember, this is, I guess we're looking at this from the perspective of R1 getting over to R4. All right, that's the one part that we're missing on this diagram. You know, it could be either way, but let's go ahead and make the assumption that it's from R1 to R4, and there's some network on R4 that we're trying to reach. So if I'm trying to figure out whether this top path meets the feasibility condition, what metric am I trying to calculate in order to find that out? I'm going to try and calculate the metric from R2 over to R4. Remember, it's from the neighbor to R4. That's the reported distance. So I'm going to try and make sure that the metric for the path from R2 over to R4 has a lower feasible distance, which becomes the reported distance to R1, than the path going this way. All right? So let's do that calculation. We already know that the worst bandwidth along the path, even if I'm just taking these two links into account, is 10 megabits per second. So we've already got that calculation. That's 256,000. So the only thing left is to do the delay calculation, which is 6,000. Keeps opening the calculator there. 6,000. I'll close that in a minute. 6,000 divided by 10. Oh no, it's already in microseconds. Tens of microseconds. Times 256. So 153600. All right. I need to add that to my 256,000. And I get 1792000. Does it meet the feasibility condition? The answer is yes. This number here, which is, yep, this number here is the metric from R2 to get to R4, that number is smaller than the overall feasible distance of the primary path, 1.8. So that means the 1.7 is this is going to qualify as a feasible successor. All right. So we've already talked about the feasibility condition. I hate this slide. This is like one of the worst slides in the entire course because how are you supposed to infer what feasibility condition is based on this particular slide here? It's really confusing, so we're not even going to go into that one. So they give you some simple numbers now. All right, looking at this topology, they're just kind of making up whole numbers to represent the condition here. We can see that we have essentially 3 paths to reach the 10.0.0.0/8 subnet. The top path has a feasible distance of 40. The middle path has a feasible distance of 31. And the bottom path has a feasible distance of 100, 10, 20, 30, 40, 140. Now, they're not adding the cost of this network for some reason in this diagram, but technically this network should also be included. It's common to all three, so that this guy's going to have a distance of 40, this guy's going to have a distance of 31, this guy's going to have a distance of 140. Based on that, which path becomes the successor path? The middle path, right? The middle path is 31, the top path is 40, so the middle path is going to be chosen as my successor. All right? I don't know why they didn't add the last. You always consider the final destination as well as part of the metric. So I'm not sure. Well, okay, so they did it here. I don't know why they didn't do it on the last slide. They were doing reported distances. Reported distances from whose perspective? I was assuming that they were doing all of this based on router 1 getting to this destination. So the reported distance, okay, yep, that's exactly what they're doing. Reported distance from R8 I'm trying to think of where they're coming up with this number. The neighbor is R8, so the reported distance, I get it. Our reported distance is the 20 plus the 10, which makes sense. That is the feasible distance for R8 to reach this network. And then you have to, of course, add the cost of this link to get your overall feasible distance. So that's how they decided to do this. And then the reported distance for this link is 10 plus 1, which is 21. Add the cost of 10, that gets me my 31, and so on. You guys understand now. So that's what they're. So we know that the successor path. The successor path in this case is whichever path has the lowest feasible distance, which is this middle path through R2. Question: do either of these other paths qualify as a feasible successor? Based on the feasible distance of the primary path, do these other two paths qualify as a feasible successor? Anybody? You got a 50-50 shot, yes or no? The answer is yes, right? The top path qualifies as a feasible successor. Remember, this is all from the perspective of R1 reaching this destination. The reported distance of the top path is 30. The feasible distance of the successor path is 31. So yes, this top path barely, but it does, meets the feasibility condition, which means that the path through R8 is going to become a feasible successor. The path through R4 definitely doesn't meet the condition because we got a link of a cost of 100 plus 10 plus 10 plus 10. So that reported distance is 140 in this case, or 130, excuse me, and the overall feasible distance is 140. So in that being said, the successor is the middle path, the feasible successor is the top path, and then the bottom path is a non-feasible successor route, and a non-successor route in this case. Not that it can't be used, but it's going to require a secondary check to make sure that that path is is going to end up being a valid path in our particular case. All right. All right. So that concludes that lesson. A lot of good stuff that we talked about in that lesson. A lot of really well, engineering type stuff about EIGRP. And really that's the most complicated discussion of EIGRP that we're going to see in the entire course. Because it includes all of the algorithm, what the algorithm is doing, how it's making decisions, and so on. So we're going to take a break, and then we're going to get into the next lesson, which is really just more of a process of just simply kind of identifying how EIGRP can be optimized to make it more scalable, to make it work a little bit better. We're going to talk about the query process and what stuck inactive is and how queries can affect the overall efficiency of the network. That's going to be our third lesson. So we'll see you guys in the next lesson.